When last we spoke, I gave you sort of a refresher of the mathematical techniques of trigonometry. And the reason why I did that is that I wanted to be able to take motion in 2 dimensions and decompose that motion into separate one-dimensional motion problems. One-dimensional motion problems are problems that I know how to solve. I use my kinematic equations. V is equal to V0 plus AT, X is equal to X naught plus V0 plus 1 half AT squared. V squared is equal to V naught squared plus 2A delta X. Using those kinematic equations, I can solve problems in 1 dimension. But when I have my marker here and I throw it through the air, I give it an initial velocity with my hand that is not horizontal, it is not vertical, it is both simultaneously. And so it flies through the air in a curved path. And that curved path is typically attributed to gravity. When an object moves in 2 dimensions solely under the influence of gravity, we call that a projectile. And projectile motion is inherently 2-dimensional motion. There are lots of examples of 2-dimensional motion that we could do, but in order to practice this skill and learn how to apply it in our physics, we're going to focus on projectile motion specifically. I want to understand the motion of objects when gravity is changing the velocity, not just in 1 dimensions, but in 2 dimensions. And the critical thing here is that velocity is a vector. As such, it not only has a magnitude, that is an amount, so many meters per second, but it also has a direction at every instant in time. Imagine that when I launch a projectile like this marker and it flies through the air, imagine that it has an arrow mounted on it that points in the direction that it's moving. That arrow is constantly changing direction during the motion. That arrow is constantly changing length, magnitude during the motion. So it's quite complicated. And I'll solve that problem by making an observation about the nature of velocity and indeed displacement and acceleration as well. In projectile motion, the vertical motion of a projectile is independent of the horizontal motion. The 2 motions happen at the same time, but they do not affect one another. The horizontal velocity has no influence on the vertical velocity whatsoever. And indeed, the force of gravity is entirely vertical. There's no part of gravity that is sideways. That's why when I simply jump up in the air, I accelerate only vertically, and I don't accelerate horizontally. If that starts happening, something really, really terrible is going on to the Earth and to the solar system. So I'd like to do a little demonstration here so that you can see that this is actually true. I have a little gizmo here in my hand. You see it again on the screen there. It is a projectile launcher, and it launches 2 projectiles. It launches 1 projectile horizontally. And so I'll shoot a projectile that way toward the front of the room. But it also drops a projectile vertically at exactly the same time. Now, a remarkable thing is going to happen. Both of these projectiles are influenced by the force of gravity. They'll both fall to the floor eventually. But one of them also has a horizontal component to its velocity. One projectile is launched towards the front of the room, and the other projectile is dropped vertically. The observation that I want you to make is that because the vertical motions of the 2 projectiles are identical, they'll hit the floor at the same time. So that's what I want you to observe here. When I launch these 2 projectiles and accidentally drop one, I knew that was going to happen. I just spent too much time talking. Would you grab that for me, please? So I don't have to get down off the... Yeah, take your time. It's not a big deal. I want you to observe them hitting the floor at the same time. But you can't look at them hit the floor at the same time because you're not a hammerhead shark. One's going to land over there, the other one's going to land over here. How could you watch them hit at the same time? So what I want you to do is I want you to listen for them to hit the ground at the same time. Oh, the ground. Look at that, Darcy. I said the ground. See that? So you're influencing me more than I'm influencing you. That's not how it's supposed to... Okay. So they're going to hit the floor at the same time. So we want to listen for that. All right? 3, 2, 1. Despite the fact that one of the projectiles is launched horizontally, travels a greater distance. Did you find that? That's right there. One is launched horizontally and travels a greater distance. Did you hear they hit the floor at the same time? Here it is shown on this slide, sort of stroboscopic photography. They activate the thing, and the yellow projectile flies horizontally as it falls, while the red projectile is simply dropped vertically. Now, the photographs are taken at the same instant in time. Look at, for example, this red marble here, and the line directly under it. If I go directly across, I see that the yellow marble has the same vertical position because it's fallen the same distance in the same amount of time vertically. Yes, it has also traveled horizontally, but the vertical motions are identical. The vertical motions are identical, and the red marble has no horizontal motion, and the yellow marble does have horizontal motion. The observation here about the nature of our universe is that the horizontal and vertical motions of a projectile can be treated separately. They are independent, the one from the other. Now, this is not always obvious, particularly if the velocity of the projectile is quite high. Imagine if I have a gun, and the gun I have a bullet, and I have a bullet in my hand. At the same time I fire the bullet, I drop a bullet. That experiment is a little bit more difficult to see what's happening there or to understand that it's the same thing because the bullet travels at such a high velocity. The bullet will travel across the room and hit the wall before it hits the floor, but that takes a very, very short period of time. In that amount of time, the bullet that I drop from rest will fall the same distance. A bullet over a short distance travels pretty much in a straight line. But I think we're all aware that the further and further and further and further and further away the target is, I have to start aiming high to account for the fact that the bullet's going to drop on its way to the target. A bullet is a projectile moving under the influence of gravity. If I were able to go to that place, there's you always see car commercials. It's the Great Salt Lake there where it's just a salt flats. It's not Great Salt Lake, that's a different thing. But the salt flats and they drive cars around real fast, whatever. Or where they do Burning Man, like that. I'm going to drop a bullet and fire a bullet. Those two bullets would hit the ground at the same time because the vertical motions and horizontal motions are independent one from the other. It's really rather remarkable observation. And I'm going to take advantage of that to solve new kinds of problems that I couldn't solve before. Because if I can separate projectile motion into the horizontal motion and vertical motion, I can solve those problems separately. And those are problems that I know how to solve. Imagine that I have a table here and I roll a marble off the table. Here I have shown the velocity vector as the projectile rolls off the table and travels to the floor along a curved path. It's quite complicated. You see exactly what you'd expect. There is an initial velocity, which is signified by a green arrow here. The arrow, the length of the arrow, is the magnitude of the velocity, and the direction the arrow points is the direction of the velocity. But as it travels to the floor, you see that two things happen. The velocity vector arrow turns as gravity turns the direction of the object towards the floor. So the arrow starts to point more and more and more and more and more towards the floor as it travels, but also the length of that vector gets longer and longer and longer and longer as it goes. So it's quite complicated, but it's less complicated when I observe the behavior of the components. Here, I have the velocity vector at the initial position, Vx naught, I guess you would say, and it's entirely horizontal. So you could say at this point that it has no y component. But an instant later, gravity has turned the velocity vector downward here, and it now has two components, a horizontal component and a vertical component. Notice that the vertical component points downward. That makes sense, because it's going downward. Now, here's the critical observation. Well, there's two critical observations. Notice that as I go from instant to instant in the motion, the horizontal component of the velocity does not change. That's a critical aspect of projectile motion. The horizontal component of the velocity does not change. And that's because there is no horizontal acceleration. The acceleration that is caused by gravity is vertical. So there is no horizontal acceleration. If there's no horizontal acceleration, then the horizontal velocity of a projectile does not change. The total motion may appear complicated. The x-axis motion, the horizontal motion, is incredibly simple. For a projectile, the horizontal motion is motion with constant speed. And that's an easy problem to solve. Looking at the vertical component of the motion, that is the y component of the velocity as we go, it starts out 0. The initial y component of the velocity is 0. It's not going vertically at the start. It's only going horizontally, not vertically in any way. But then, once it leaves the table, gravity exerts its influence, and the vertical component of the velocity grows ever larger as the projectile goes toward the floor. Getting longer and longer and longer, the vertical component of the velocity increasing in time because gravity causes an acceleration of 9.8 meters per second squared. And so the vertical component of the velocity is affected by gravity. And that velocity increases as it goes. But that's free fall. And you see right next to it, the vertical fall is shown. If I just drop the thing and let it fall, notice that the y components of the velocity are the same in every instant of time. In projectile motion, the vertical motion is the same as free fall motion. And that is a problem that I can solve. Speaking of problems that I can solve, I'm going to revisit this again at the end of the presentation. So, now I'll do it now. What the heck? That was just going off the edge of the table. This motion, a little more sophisticated. The particle starts out here at 0. I'm going to launch it. It's like a cannonball or something, or a football thrown, or a baseball hit off a bat. And it has an initial velocity that is not horizontal. It is not vertical. It's both. And so what I do is I use my trigonometry skills to break that initial velocity down into its horizontal and vertical components. Here's the horizontal component of the velocity, Vx naught, written right here. I notice that it is adjacent to the angle. So trigonometrically, I'm going to find this part, the horizontal part, using cosine, and I'm going to find the vertical part using sine. As the projectile goes along, notice, just like the instance when it rolled off the table, that the horizontal velocity is constant. The horizontal velocity in projectile motion does not change because the x-axis, the horizontal acceleration, is equal to 0. The horizontal motion of a projectile is motion with constant velocity. Very easy to solve. Notice what happens to the vertical motion. The initial y velocity is quite large, but as it rises, it gets shorter, and then eventually at the highest point, the y component of the velocity is equal to 0. Not the whole velocity, but the vertical part is, because it has stopped rising and will begin falling. As it falls, the vertical component of its velocity will become probably negative, depending on how I choose my coordinates, but it becomes downward, and even greater downward. Notice that there's a lovely symmetry to this. Because the projectile goes up and down by the same amount, you see it's symmetric, it arrives at the same height from which it was launched. The initial y velocity and the final y velocity are the same, just in opposite direction. That's because projectile motion is symmetric. Freefall motion is also symmetric. You've probably encountered a problem in your homework where a thing is thrown upward and it goes up and down, and the time it takes to rise is the same as the time it takes to fall. The same thing's happening here. The time it takes a projectile to rise to its maximum height is equal to the time it takes to fall. The velocity that a projectile loses on its way to its maximum height is the same as the velocity that it gains as it falls back down again. The motion is symmetric in time and space. So now I need a problem to solve. I'm done with all of the theoretical mumbo-jumbo, and I need an actual projectile motion problem I can solve. I'm going to start with an easy one. The reason why I know that this is an easy projectile motion problem to solve is that here's a motorcyclist. This is crazy. You don't often see this in a physics textbook. There's clearly where I got this diagram. The motorcycle is going off a cliff, and the cliff is 50 meters high. You don't survive this. Usually physics problems are written in such a way that it's very survivable. But perhaps what I'm doing here is a theoretical approach to this so that maybe I can build some sort of a ramp or a landing platform or something to see if we can survive this. I may be able to comment on that after I'm done my analysis. But what I know about this is that the motorcycle goes off the cliff, and like a projectile, it follows a curved path, which turns out to be a parabola. It follows a curved path to the ground where it lands 50 meters below where it started and 90 meters from the end of the cliff. Notice that is a description in 2 dimensions. 50 meters down, 90 meters over. Y-axis, x-axis. There are things that are unknown in this problem. I'm going to do what I usually do. I'm going to find everything that is unknown about the problem and a bit extra. In order to analyze this motion, I'm going to break it down into two one-dimensional motion problems. Anytime I solve a one-dimensional kinematics problem, I need a list of known quantities. If I'm going to do two problems, then I need two lists. Look what I've done here. I have a list that is very familiar. X naught, x, v naught, v, time acceleration. Except I've added a little bit. I have to specify when I'm talking about the velocity that it is the x velocity. And here, the initial x velocity, here the final x velocity. And also with the acceleration, I have to specify that I'm talking about the x-axis acceleration. Because the quantities that go on this list are not the quantities of the motion, they are the components of the quantities of the motion. Similarly, when I make my vertical list, my y list for the motion, it's all the same quantities you'd expect, but in the context of the vertical axis, the y-axis. So y naught y, vy naught, vy, time, and acceleration along the y-axis. I have to have this much notation because I have to keep these things separate. I have to keep them clear. It shouldn't be that big of a problem because the only place where they cross over is time. The horizontal motion and the vertical motion take place at the same time. So whatever I find for the time on the x list is also the time on the y list and vice versa. In fact, that sometimes is a strategy for solving problems. Find the time on one list so that I can find something else that I want on another list. So exchanging the time between is often a problem-solving strategy. So when I look at this problem description, I need to fill out my lists according to what I see in the physical description. But now I've got two lists to go through. It works the same way. I go down the list and I ask myself, do I know this physical quantity? And I fill in the list accordingly. So, going down the X list, well, I skipped a step, didn't I? I skipped a step because I'm supposed to choose a coordinate system. So I draw a picture and choose a coordinate system, and I neglected to mention that step. Now when I choose a coordinate system, because my problem is two-dimensional, I'm not just choosing the x-axis positive direction, but also the y-axis positive direction. And that's just as easy to do as it was before, except now I signify both the x and the y directions. I show where I choose 0, and nobody's surprised that I would choose 0 to be the initial position of the motorcycle. Some people might disagree with that choice. They might say, well, I want to choose it at the bottom of the cliff. You can do that, that's no problem. You'll get the correct answer. It doesn't cause any trouble at all. The choice of coordinate system is always arbitrary. Well, I haven't filled out the list yet. I'm just choosing my coordinates. And then we'll talk about how I fill things out, which is a mistake that I make. I was ready to go onto my list without having chosen the coordinates, and so it's difficult to explain why I choose what I do. So I choose the initial position of the motorcycle to be 0, and since gravity is involved, I always choose upward to be positive. That's the same deal as before. I always choose upward to be positive because if I choose upward to be positive, then the acceleration due to gravity when it makes its way into the problem is always going to be negative 9.8 meters per second squared. So I will always choose upward to be the positive direction. But Shadi, the motorcycle goes down. Always I choose upward to be the positive direction because that reduces the number of choices that I have to make when I'm solving a problem, and that reduces my chances of making a mistake. So I choose the regular sort of math coordinates. I put my origin where the motorcycle leaves the cliff, and I choose upward and outward to be positive. And now, fill out the list. So I'll start at the beginning of the position list and say, what is the initial position of the motorcycle? Well, I chose it. It's 0 meters. I chose that the initial position of the motorcycle should be 0 meters. What is the final horizontal position? When I'm filling out my X list, I don't care anything about the vertical displacement, only the horizontal displacement. The 50 meters means nothing on my X list. The motorcycle going from the top of the cliff to the bottom of the cliff where it lands travels horizontally 90 meters. So the final position along the x-axis is 90 meters. What is the initial x velocity? How fast does the motorcycle go off the cliff? I have no idea. It's one of the things I'll find in the problem solving, so I put a question mark there. I also do not know what the final horizontal velocity is when the motorcycle reaches the ground at the end. I don't know that horizontal velocity. How long does it take to reach the ground? I don't know. This is getting a little upsetting. I don't have any information. That's very true because the x-axis acceleration, the horizontal acceleration of the projectile, is 0. The horizontal acceleration of the projectile is 0. That means that the horizontal velocity doesn't change, and that's a thing that I already knew about projectile motion. I realized looking at the motion graphs that the horizontal component of the velocity does not change during projectile motion. The acceleration is 0. It will always be 0. In every problem that I ask you to solve in this physics course, AX will always be 0. The horizontal component of acceleration is always 0. So why put it on the list? Well, for the sake of symmetry and completeness. In reality, it's not always 0. In fact, in reality, it's not, in fact, 0. But in our simple model of projectile motion, particularly where we ignore air resistance, the horizontal component of the acceleration is equal to 0. So Aaron's observation is correct. Whenever I find them, these two velocities will be the same. Not only in this problem, but in every problem that I solve. These two will always be the same. Now, I change my thinking from the horizontal motion to the vertical motion. Here is my vertical list. It begins with the initial vertical position, which is also 0. I chose my vertical and horizontal 0 to be at the same location in space. I don't have to do that, by the way, but keeping the confusion to a minimum, it makes sense to do that. I choose the initial y position to be equal to 0. The final y position, you have to be careful, because the cliff is 50 meters high, but I chose the initial position to be at the top of the cliff with upward positive, which means I go down 50 meters, which means the final y position is negative 50 meters. That's critically important. You realize that if I don't get that right when I'm making my list, this physics problem is going to go wrong for me. Just like with one-dimensional kinematics problems, all the physics happens on the list. This is where I make all the decisions. This is where I do all of my thinking. And afterwards, I'm going to do math to find answers. So the final y position is negative 50 meters. What is the initial y velocity in this problem? The initial y velocity is equal to 0. And the reason why is that the motorcycle is going off the cliff completely horizontally. At the beginning of the problem, the instant it leaves the cliff, it is not moving up and down. It is only moving horizontally. And since it's only moving horizontally, the vertical component of its velocity, the y component of its velocity, is 0. In this problem, that, by the way, is what makes this a simple projectile motion problem. If the projectile is launched from the top of the cliff at an angle, then it has an x component, like this motorcycle does, but it also has a vertical component. And that makes the solution of the problem a little bit more challenging. But walk before we can run off a cliff. So the initial y velocity is equal to 0. What is the final y velocity? Charlie, it's 0 because the motorcycle smashed into the ground and the guts splatter all over the place and the velocity is 0. Not when it gets there and hits the ground and stops. I'm talking about the vertical component of its velocity just when it arrives. The collision with the ground is a different kind of physics, which we can solve, by the way. But I'm talking about the velocity the instant it reaches the ground, and that's not 0. I don't know what that is. I didn't know the time for the x-axis motion. I don't know the time for the y-axis motion. But when I find it, it is the same for both. What is the acceleration? Because I've chosen upward to be the positive direction, I know that the acceleration on my list is negative 9.8 meters per second squared. I've filled out my lists. Since I've got my lists filled out, that means I'm ready to solve the problem. But in order to solve the problem, I need equations. But this is just two one-dimensional problems. It's just two one-dimensional problems. It's a horizontal motion problem where the acceleration is equal to 0, and it's a vertical motion problem that's a free fall problem. And I know how to solve those problems. And so, I have equations to solve them already, but I might make some modifications. When it comes to the horizontal motion of the projectile, there's only one equation that matters. There's only one equation for the horizontal motion of a projectile, only one. I've got 3 kinematic equations. I mentioned them at the beginning. V is equal to V naught plus AT, X is equal to X naught plus V 0 T plus 1 half AT squared, and V squared is equal to V naught squared plus 2A delta X. But if you look at that set of 3 equations, when the acceleration is equal to 0, as it is in horizontal motion, when the acceleration is equal to 0, the only equation that survives is X is equal to X naught plus V 0 T plus 1 half AT squared. The 1 half AT squared part is missing from the equation because the acceleration is 0. So very simple solution for the horizontal motion. There's only one equation. For the vertical motion, there is acceleration, and so the equations look a bit more complicated. But notice that these equations are the same three kinematic equations I've been using the whole time. They've just been modified in terms of their notation to explicitly describe the vertical axis of the motion, that is the y-axis of the motion. So instead of x is equal to x naught plus v naught t plus 1/2 at squared, I have y is equal to y naught vy naught t plus 1/2 ay t squared. To match the quantities on my list, it's the same three kinematic equations, but written according to the y-axis. These are the equations that I solve. Now, when I'm solving problems of projectile motion, it is most common, not always, but is most common to start the solution on the y list. It's most common to start with the y list first. There are a few problems out there where you start on the x list, but it's common to start on the y list, and so that's what I'm going to do for my problem solution. I'm going to find the things that are unknown on my y list. That means I'm going to find the final y velocity, and I'm going to find the final time, and I do it using simple kinematic equations as I've gone along. Let's find the time that it takes the motorcycle to fall vertically to the ground, which is also the time that it takes the motorcycle to travel horizontally to the ground. The time is the same for both motions. So I'll start with y is equal to y naught plus vy naught t plus 1/2 ay t squared. And realize that my list says that the initial y position is 0 and the initial y velocity is 0. And so this equation becomes simple, which is why I said that this is a simple example of projectile motion. Explicitly why this problem is easier to solve than some others you might encounter. So I solve this algebraically for the time. And I get that the time it takes to fall is equal to the square root of 2y over ay. And that's a familiar equation, because that's the equation that I used to figure out the time it takes for an object to fall when I was doing uncertainty in measurement and dropping things down stairwell. So I plug in the numbers from my list. Y on my list is negative 50, but that's okay, because the acceleration is negative 9.8. Those negatives cancel. Of course, I need to be taking the square root of a positive number, and it works out that way, so I have confidence. And I get a time, 3.2 seconds, which is rational, makes sense. Now that I know the time, I can take that time and move it over to the x list. But before I do that, let's find the final y velocity. The final y velocity is still unknown on my list. I now know that this is 3.2 seconds, and it's therefore 3.2 seconds over here. But the y velocity, I'd like to calculate. So I use a kinematic equation. In particular, I use that vy is equal to vy naught plus ay times t. That's the equation that I choose to use here. And I appreciate the fact that vy naught is equal to 0, so the equation is quite simple. Vy is equal to ay times t, so negative 9.8 times the time, 3.2, that I just found, is negative 31.4 meters per second. I got a negative final vertical velocity, and that makes sense. Because when the motorcycle arrives, the canyon floor, it is traveling downward in a vertical sense. And since I chose upward to be the positive direction, a downward negative velocity. Makes sense. Units of meters per second. And so my entire y list is figured out now. I've learned everything on the y list. Now I'd like to go and look at the x list. On the x list, there's only one thing that's unknown. We say, well, no, it's 2. It's not 2. It's one unknown thing, because there's only one velocity to solve for, because the horizontal component of the velocity in projectile motion is a constant. It does not change in time. And I only have one equation to use. X is equal to x naught plus vx times t. So if the initial position is equal to 0, which my list describes that it is, x is equal to vx times t. I'll simply solve for vx, which is x over t. 90 divided by 3.2 is 28.1 meters per second. 28.1 meters per second is vx naught, which is also vx. And now my list is complete. Fantastic, I found everything. Yay. No, I haven't found everything, because I didn't find the final velocity. I didn't find the final velocity. No, Charlie, yeah, you did. It's negative 31.4 meters per second right there. You wrote on it. That's not the final y velocity. That's the final velocity's vertical component. That's the y component of the final velocity. Oh, sorry, Charlie. I meant 28.1. You found 28.1. That's the final. That's not. That's the x component of the final velocity. Because my motion is two-dimensional, I solve it by taking the two-dimensional motion and breaking it up into two one-dimensional parts. When I get to the end of the problem, I've got to put it back together again. Here I am zoomed in on the final location. This is where it hits the ground. When it hits the ground, it has a horizontal velocity of 28.1 meters per second, a vertical velocity of negative 31.4 meters per second. Yeah. Well, not necessarily trigonometry, but, well, yeah, because this is a right triangle. You say, well, Charlie, it doesn't look like a right triangle. Yeah, but it is. Because if I move that one velocity arrow over, it now forms a right triangle, and I can find the magnitude of the final velocity. It's a right triangle. 28.1, negative 31.4. I apply the Pythagorean theorem to it, so it's 28.1 squared plus 31.4 squared, square root, and I get 42.1 meters per second. Woo! I found the final velocity. No, I didn't. Velocity is a vector. It's a magnitude and a direction. And I haven't found the direction yet. I can't say that the direction is negative. Because what is negative? I guess negative would imply maybe it's straight down. It's not straight down. It's at an angle, isn't it? I have to find that angle. And I find that angle using the inverse tangent. This is how I do. The angle is the inverse tangent of the y component of the velocity divided by the x component of the velocity. Inverse tangent. And that gives me the angle relative to the horizontal. So I do that calculation, 31.4 divided by 28.1. Shadi, you made a mistake. You didn't put a negative sign on the 31.4. When I use the inverse tangent on my calculator, I never, ever put negative signs in it. My calculator doesn't know that I'm doing physics, and my calculator has funny ideas about angles. If I put negative signs inside an inverse tangent in physics, I could get some wild angle answer out of my calculator that I have to interpret. So what I do instead is I interpret the angle and I just have my calculator do the arithmetic. If I always put positive numbers in the inverse tangent, I'll always get an angle between 0 and 90 degrees. And that is the easiest way for me to interpret. I suppose it's possible now that I know what the angle is, it's 48.2, that I could build a ramp that would allow the motorcycle to safely land. So ended the lesson.